In this problem, we're asked to calculate the exact molarity, the actual molarity of a sodium hydroxide solution. When you go through that process in lab and you do the supporting calculations, that's known as standardization. So the word standardize is used to standardize the sodium hydroxide solution. This word means to find the exact concentration. Why would somebody have to do that? Why couldn't they just base their concentration off the mass of the sodium hydroxide and use really nice glassware and a nice scale? Wouldn't that be enough? Well, the problem with sodium hydroxide is that it's hygroscopic. So it's insane. I wish I had a sample to show you all, because usually when we do this lab, I'll show the students the sodium hydroxide at the beginning of the lab period. It's dry. It looks like little pellets. But by the end of the lab period, if I leave it out in a little dish, it turns into a puddle. So it just pulls in all the moisture in the air. So since it's hygroscopic and absorbs water, the mass cannot be trusted. We don't know how fast that's happening. So if we're weighing out like 2 grams of sodium hydroxide, is it actually 2 grams of sodium hydroxide, or is it 1.8 grams of sodium hydroxide and the rest of it is some water that's been absorbed? So we try our best, and that's why in the beginning of this problem it says a solution of sodium hydroxide is supposed to be 0.100 molar. So somebody who's aiming for that, but because of the hygroscopic nature of the sodium hydroxide, it's a questionable value. We're not going to use that in our calculation. So that's why I wrote on top of it, cross it out. We're looking for some value that's probably going to be very close to that, but we don't want to use that value at all. All right, and so the last part here is that we're using KHP. So KHP is a monoprotic acid, and the most important part though is that it's an acronym. This will be the main way. Students will do such beautiful work, and then they'll look at KHP and think that it stands for potassium, hydrogen, and phosphorus. No, it's not potassium, hydrogen, phosphorus. It actually has this crazy formula right here. It's a pretty big ringed structure. So look on the bottle. The molar mass of the KHP is 204.22 grams per mole. And I'm pulling that from memory even. That you use so much KHP. You have to standardize so much when you work in any kind of lab setting that's why I actually even know that, because we just use this process so much. It's really important because if we think about it, the sodium hydroxide is then going to be used to verify the concentrations of other solutions. So I want to be confident in my sodium hydroxide before I use that in next steps. So if you do want to calculate the molar mass yourself and verify my number, you would use this formula here. So I mentioned that KHP is a monoprotic acid. That means it donates one H, one hydrogen. So it's going to react in a 1-to-1 ratio with sodium hydroxide and form water on the other side. It's going to be an acid-base neutralization reaction. There is an equation on your sheet there with this problem. It shows the ionic equation, and you can look at that to figure this out as well, but you should also know, just from experience after a while, that it's going to react in a 1-to-1 ratio. I didn't try to pronounce the KHP. It's like potassium hydrogen phthalate. I hate saying it because the third word, the P, is PHT, and I never know how to pronounce that combination of letters. Everybody just says KHP. I'm going to use a T-chart here, just like I did in my other acid-base problems. And I usually go for a T-chart when there's a lot of information, when they start throwing molarities in there. I just like to use it to organize my thoughts and extract what I need from all this blah, blah, blah. So I'm going to ignore that first value. That's just them telling me, they try to shoot for 0.1 molar. It is important I have 0.500 grams of KHP. And KHP doesn't absorb the water like sodium hydroxide. So we can count on that being actually 0.500 grams. It doesn't have that same problem like sodium hydroxide. And then they did their titration, and they used an indicator probably and all that. It looks very similar to other titrations. And they needed 24.03 mils of the sodium hydroxide solution, and they want us to find the molarity of the sodium hydroxide solution. I always, once I get my information in my T-chart, I always begin with the same question. Can I solve for moles on either side? So over here, I don't have moles. I don't have molarity, so I'm kind of stuck with this sodium hydroxide. I don't have enough information. However, on the KHP side, we do know the molar mass. So the mass that they used along with the molar mass can get me the moles of KHP. So I'm going to set that up. So I have 0.5000 grams KHP, and there's 204.22 grams in 1 mole of KHP. And that's going to give me the moles of KHP. So I'm looking at 2.44834 times 10 to the negative third moles. Of KHP. All right, so that value can go over here if I want. And because it's 1-to-1, I can set up the conversion, and I'll do that really quickly just to show how that looks. But in my head, I know that if I have this many moles of KHP, since they react in a 1-to-1 ratio, I'm going to have the same amount of sodium hydroxide. Because the moles of KHP will cancel the moles of KHP, and that gives me 2.44834 times 10 to the negative third moles of NaOH. So then I can come over here. Now I have moles. I'm going to divide this by 1,000 to turn it into liters. So my molarity then is going to be 2.44834 times 10 to the negative third moles of sodium hydroxide divided by 0.02403 liters. So I'm using this value divided by 1,000 because we always need liters in our molarities. And at the end of the day, after I divided those numbers, I got 0.1018868 molar. Looking at sig figs, all of these values have 4 sig figs. Again, this number doesn't mean anything. It's kind of what they were shooting for when they prepared the solution, but it's not a value that I use, so I don't have to worry about the fact that it only has 3 sig figs. The mass had 4 and the volume had 4, so I can report my final answer to 4 sig figs. So I'm going to do 0.1019 molar sodium hydroxide as the concentration of the standardized solution. Alrighty, so in this problem, we're asked a couple different questions. First, how many grams of sodium sulfide are required to react with this silver nitrate solution? And I know it's a solution because they gave me a molarity, but also in the reactants of the equation, it's listed as aqueous. So we haven't seen precipitation reactions involving solids, but it kind of makes sense what's going on here, because once you start putting the sodium sulfide into the aqueous silver nitrate, there's a lot of water in there. So the sodium sulfide we know is normally soluble, right? It's normally aqueous, and it's going to dissociate into its ions. So it's going to be available for reaction once we mix it with the aqueous silver nitrate. Let's predict the products. So silver is going to be a +1, and nitrate will be a -1. And sodium, well, I don't want to put that 2. That 2 belongs to sulfur or sulfide because it's in group 6. Sodium's in group 1, so I know that that does a +1. And so that makes sense because the 2 came down that way. It's not part of sodium. I'm going to do-si-do them. So we're going to combine silver and sulfide and sodium and nitrate. So when I do silver with sulfide, there's that 2- on the sulfur, which would come down and serve as the subscript for my silver. So this is going to be Ag2S. And most compounds containing silver are going to be solid. So this is probably going to be my precipitate. And then for the sodium nitrate, it's +1 and -1. So the crisscross isn't too important. But I need to put the sodium first, in front. And both of those ions are associated with aqueous compounds. So I'll label that as aqueous. So it's looking good so far. I need to remember to balance this because that's going to enable me to figure out everything else. So I have 2 sodiums here. So I'm going to put a 2 here. That gives me 2 nitrates. Right now I only have 1 nitrate, so I'm thinking of this in its entirety. So if I put a 2 here, that'll give me 2 nitrates and then 2 silvers. But I'm okay, I have 2 silvers and then the 1 sulfur. So it's balanced and I'm ready to fill out the rest of the information, get organized here. So how many grams of sodium sulfide solid? So here we're asked to solve for grams, are required to react completely with 27.8 milliliters of 0.163 molar silver nitrate. Moles, I always want to get to moles. All right, I definitely have enough information on the silver nitrate side to solve for the moles of silver nitrate. So molarity is moles over liters. So if I do liters times molarity, that's going to give me moles. I need to divide this by 1,000 then, so it's liters. And I'm going to do 0.0278 times 0.163 molar. And I'm going to wind up with 4.5314 times 10 to the -3rd moles of silver nitrate. Now remember, this is going to work the same way as your acid-base titrations. You can't move a value from this side of the T-chart to this side of the T-chart without considering the mole-to-mole ratios in your balanced equation. So I'm going to take this value, 4.5314 times 10 to the -3rd moles of silver nitrate. And I want to get rid of moles of silver nitrate. And I'm trying to figure out how much sodium sulfide I need. So I'll do moles of sodium sulfide in the numerator. So that's canceling with that. And then I'm going to grab the coefficients of the balanced equation. So out here, I would have had a 1. It's understood. And then over here, I have a 2. So let me check my units and see where I'm at. Right now, moles is canceling with moles. So if I stopped right now, I'd be at moles of sodium sulfide. It's good to know, but they asked me for grams of sodium sulfide. So I'm going to do the molar mass of the sodium sulfide. So what is that? 23.00 grams. There's 2 of them. And then the sulfur is 32.07 grams. So I'm looking at a molar mass of 78.07 grams per mole for my sodium sulfide. And so you could absolutely do it in 2 steps, but I always encourage students minimize the steps. It just makes life easier, especially as you get to bigger and bigger and bigger problems. So I'm going to use my molar mass value to get my answer here. So 1 mole of sodium sulfide has 78.07 grams of sodium sulfide. And now my units are grams of sodium sulfide. That's great because that's what I want. And when I did that, I got 0.176883 grams of sodium sulfide. I only have 3 sig figs, so I'll report my answer for part A as 0.177 grams of sodium sulfide. Part B says how many grams of the precipitate are formed. So the precipitate is a solid that formed after the double displacement reaction. So the precipitate is going to be my silver sulfide. In order to calculate the grams of silver sulfide, I'm going to need a molar mass for that. I'm going to put the molar mass up here because I'm running out of space. So we have 2 silvers. I'll do 107.87 grams times 2, and 1 sulfur. So that gives me a molar mass of 247.81 grams per mole for my precipitate, for the silver sulfide. So again, this will be a mole to mole ratio. For me, the easiest jumping off point would be to start with the moles of silver nitrate that we calculated earlier. So I'm going to rewrite 4.5314. And again, it always goes back to thinking about moles as being your bridge to where you want to go. So that's why I'm going back to one of my original or earlier mole values. So I'm trying to get rid of moles of silver nitrate. And I would like to turn it into moles of silver sulfide. And I need to look at the coefficients of my balanced equation. So I have 2 moles of silver nitrate for every 1 mole of silver sulfide. And just like in the previous example, we can take this one step further since they wanted us to solve for grams. So I'll do 247.81 grams of silver sulfide per 1 mole of silver sulfide. And that's going to leave me with units of grams of silver sulfide. So when I did that, I got 0.561463 grams of silver sulfide. Again, 3 sig figs. So for my answer for part B, this is my answer to part B, A. For B, I would report my answer as 0.561 grams of silver sulfide. So we have another reaction stoichiometry problem. This time they didn't even give us reactants. So we're going to have to come up with the balanced equation from the written description. So we have silver nitrate. And so I'm thinking silver is +1. It's a constant charge. And nitrate is -1. So when I crisscross those, I get AgNO3. Anything with nitrate in it is going to be soluble, so I'll label that as aqueous. And then potassium chromate, they did give us the formula for that. Since it has potassium and potassium's a group 1 ion, that too will be aqueous. I'm going to split the silver up into those ions again. Split the silver nitrate up. I'm going to do the same for the potassium chromate. So potassium's group 1, so I know that it's just +1. That means that this 2 must belong to the chromate. So I'll do CrO4 2-. I'm going to do-si-do. So silver will hook up with the chromate and potassium with the nitrate. So I have Ag plus and CrO4 2-. So this 2 is going to go down and serve as the subscript for the silver chromate. So typically compounds containing silver are solid, with nitrates and acetates being some of the few exceptions, but about 95% of the time, anything with a silver will form a precipitate. So I'm going to label that as my solid. And then my other 2 ions, potassium and nitrate, those are always aqueous. And they're 1-to-1. I just have to reorder them. So the cation is first. So I'll do KNO3 and put that as aqueous. So now that I came up with an equation, the next step would be to balance that equation. So I have 2 potassiums. So I'll put a 2 out front here. That gives me 2 nitrates. So I'll put a 2 out here. So I have 2 nitrates. Now 2 silvers. And I already have 2 silvers, 1 chromate and 1 chromate. So we're good to go with the balanced equation. Let's organize the rest of the information. Oh, we can answer this question even before we do that. What precipitate is formed? So between the 2 products, I know that the silver chromate will be my precipitate. What volume of 0.650 molar potassium chromate is required to precipitate all of the silver ion? What volume of this stuff? And then going back to the beginning, 415 mils of 0.186 molar silver nitrate. I know I'm reading through this and writing these numbers down as I read. Typically though, I have to read through it, think about my approach, read it again, organize my information. I'm never able to just extract the numbers on my first read. So don't think like, oh, like she's doing it so quick, it should be easy. It isn't. You have to sit there and really think about what belongs to what and how you should organize stuff. So here I can solve for moles, and I'll do that by doing molarity times liters. So do 0.186 molar times, we'll divide this by 1,000, so 0.415 liters. So I'm going to get 7.719 times 10 to the negative 2 moles of silver nitrate. So again, the same rules apply with T-charts. If you're on one side of the T-chart and you want to start filling in information on the other side, the only way to connect the two sides is by your balanced equation. So let's do that. We have 7.719 times 10 to the negative 2 moles of silver nitrate. I'm trying to get rid of silver nitrate and get information about potassium chromate. So I'm going to use the coefficients of my balanced equation. So I'll do 2 moles of silver nitrate and 1 mole of potassium chromate. What do they ask me for? They ask me for volume. And by all means, if it makes more sense to you to finish this solve for moles and put it over there, you absolutely can. But I really do like to get stuff done in as minimal steps as possible. So thinking about the definition of molarity, right? I'll put my thought bubble. I know that molarity is a conversion factor. It's 0.650 moles per 1 liter. So in this case, it's going to be moles of potassium chromate. And I can use that to get rid of the moles, if I flip it, and turn it into volume. So I'm going to put the 0.650 moles in the denominator. And then it's per 1 liter. And when I solved that, I got 5.937692 times 10 to the negative 2 liters of the potassium chromate. It doesn't seem very realistic to me to think about it that way, because I know if I'm in the lab, I'll probably be dealing with milliliters. So tack on another conversion factor, or just multiply this by 1,000 in your calculator. So at the end of the day, with, what do we have, 3 sig figs, I would say that we need 59.4 milliliters of the potassium chromate to completely precipitate out that silver. So this is one of those problems that if you can do this, if you successfully got the answer, then you're good to go. This is a very, very challenging problem, and it's more representative of the material that you'll see in Chem 110, but I think most of you are probably ready at this point to start putting the pieces together to some harder problems. So they're talking about this white pigment, lithopone, and it consists of the 2 products from the reaction of zinc sulfate and barium sulfide. So our first step will be to write a balanced equation for the reaction and figure out what actually is in the lithopone. So zinc, I know, has a +2 charge, and sulfate is SO42 minus. Remember, this is one that you just have to know. Zinc is going to be +2. Barium's in group 2, so that's going to be a +2. And sulfide's in group 6, so that's going to be a 2-. So these two combined will be one reactant. So zinc sulfate. They're going to combine in a 1-to-1 ratio because the +2 and the -2 are going to cancel each other out or even out. Same thing over here. We got a +2 and a -2, so we're looking at a 1-to-1 ratio. I'm writing them down as aqueous. Barium sulfide solubility is a little bit questionable, but since they're trying to mix these two things and they gave me molarities for both, I'm going to assume that they were able to make it aqueous. There are little tricks that chemists use to force stuff into solution. Alrighty, so the products, we're going to do-si-do them. So the zinc is with the sulfide, and the barium, just do it like that, is with the sulfate. So we're going to have zinc sulfide. That's going to be a solid as one of our precipitates. And the other precipitate, it's still going to be 1-to-1, but I got to put the barium first. So I'm going to do barium sulfate as my other precipitate. Double check, but this is actually balanced. So we can continue with the problem. So we have 315 mils of 0.275 molar zinc sulfate. So I already set up my T-chart, and I'm going to put the information in there. And 285 mils of 0.315 barium sulfide. This is kind of weird, right? And this is why I mentioned that this is a challenging problem. In the past, we've only been able to solve for moles on one side of our T-chart. And then we're like, okay, if we get moles over here, then we can use our balanced equation and get moles over here. Now I can solve for moles of both of these things. But let's connect the pieces. Remember a couple of videos ago, we were talking about limiting and excess reactants. So if we know the moles of barium sulfide and we know the moles of zinc sulfate, one of them is going to be our limiting reactant. So we need to go about and determine that. So I'm going to focus on, I don't know, I'm actually going to need both. But for now, I'm going to focus on barium sulfide, barium sulfate. Because remember, when you're trying to determine the limiting reactant, you want to focus on one product. So first I'll do molarity times liters equals moles. So I'll do 0.315 times 0.285, because I divided the liters by 1,000. And here I get 8.9775 times 10 to the -2 moles of barium sulfide. I'm going to do the same thing on this side, but only use the numbers from this side. So 0.275 molar times 0.315 liters. And on that side, I get 8.6625 times 10 to the -2 moles of zinc sulfate. All right, now I want to see which one of these is my limiting and which one of these is my excess. I want to calculate my theoretical yield in grams of barium sulfate. Because they asked us for grams of the lithophone, and we're going to need both eventually, but let's focus on the barium sulfate to begin. All right, so I'm going to start with the barium sulfide mole value. If I have 8.9775 times 10 to the -2 moles of barium sulfide, and then there's ones out front, so I know 1 mole of barium sulfide is going to make 1 mole of barium sulfate. do need grams. And so ahead of time, I did calculate the molar mass of barium sulfate. So for barium sulfate, we're looking at 233.40 grams per mole. 1 barium, 1 sulfur, and 4 oxygens. Eventually, we're going to need the zinc sulfide as well to calculate the grams that are formed. So that one's going to be 97.46 grams. So at this point, again, because they're asking me for grams, I'm going to take this stoichiometry one step further and convert it to grams. So 1 mole of barium sulfate has 233.40 grams of barium sulfate. So from this top line, I multiplied the moles times the molar mass, and I got 9535 grams of barium sulfate. Now, just like the limiting excess reactant problems, I need to redo that using the information about my other reactants. So I'm going to analyze zinc sulfate next. So I'll start with 8.6625 times 10 to the negative 2 moles of zinc sulfate. And 1 mole of zinc sulfate. And you know what? I'm pulling out those numbers really quickly here. I knew it was 1. There's all 1s on this balanced equation. 1 mole of zinc sulfate results in 1 mole of barium sulfate. Moles of zinc sulfate are gone. And let me just get the barium sulfate to grams. So I can use that same value, the 233.40 grams of barium sulfate. This is canceling. And so now at this point, I get 20.2183 grams of barium sulfate. All right, so let's start identifying limiting and excess reactants and theoretical yield. Just like in our previous videos, when you take your 2 reactants and change them either into moles of product or grams of product, as long as they have the same units, you can compare them. The larger one is useless. Cross out the bigger of the values. This smaller one is going to be our theoretical yield of barium sulfate. So the theoretical yield, you go back to the beginning of the problem, that's always associated with your limiting reactant. And the ones that you crossed out, or the one that you crossed out, is associated with your excess reactant. So barium sulfide is in excess. Now, limiting reactant is really important because the limiting reactant always determines or dictates how much product can be formed. So I can redo the whole process just like this, and then cross out the bigger number and all that for zinc sulfide. I need the grams of zinc sulfide because the lip opponent is zinc sulfide and barium sulfate. But you don't have to do all that. Since we already identified the limiting reactant, it's the limiting reactant for both products. And that's why when you do these problems, it doesn't matter which product you focus on because the limiting reactant is the limiting reactant. So long story short, I'm going to take my moles of this limiting reactant and use the moles of zinc sulfate to calculate the grams of zinc sulfide that I can make. So let me set up that problem. So I'll do 8.6625 times 10 to the negative 2 moles of zinc sulfate. And then 1 mole of zinc sulfate will result in 1 mole of zinc sulfide. And then because they asked us about grams, I'm going to tack on the molar mass. So the 97.46. When I did that, I got 8.4425 grams of zinc sulfide. So moles cancel moles of zinc sulfide, moles of zinc sulfate will cancel, and we're left with grams of zinc sulfide. So to finish this problem up, the lithopone consists of zinc sulfide and barium sulfate. And they asked us how many grams of the lithopone will be produced. So this value down here is like my theoretical yield of zinc sulfide. So I want to add up both of my theoretical yields. And this is a very specific case. Don't think, oh, every problem you're going to have to do something like this, case by case basis. So to finalize my answer here, I'm going to do 20.2183 grams of barium sulfate plus 8.4425 grams of zinc sulfide, and that's going to give me a total of, I rounded it to 3 sig figs, so 28.7 grams of the lithopone pigment.